Hello, we are Team 2 and our project is on facial expression recognition. We'll go over these topics in our presentation, starting with the introduction. Humans have many avenues through which they transfer information, one such avenue being facial expressions. Facial expressions can reveal a lot of hidden information, including a person's emotional state, which can be used within contexts such as psychological assessment or legal interrogation. Considering the importance of human computer interaction, a facial expression emotion classifier becomes increasingly more desirable. Even though there already exist several high accuracy models that distinguish sample expressions and emotions in simple and control settings, there's still room to improve in models that aim to identify complex emotions based on facial expressions to a high degree in a real world setting. As such, in this project, we aim to create an efficient model that classifies emotion based on facial expressions in a real world setting. This means that our goal is to create a model that can accurately classify emotion independent of age, ethnicity, and appearance of a person. This model can potentially be of great service in the medical, psychiatric, legal, and leisure industries due to the planned generality of its classifications.
Our baseline dataset is FER 2013, which was collected automatically by the Google Image Search API and is available on Kaggle. It consists of around 36,000 grayscale images of faces, which have been resized to 48 by 48 pixel scale. In the dataset, images of 7 facial expressions have been classified. They are angry, disgust, fear, happy, sad, surprise, and neutral. Now let's move to related works part. There is plenty of existing research in the FER domain. In particular, a recent paper by In-Kyu Choi, Facial Expression Classification using DeepCNN, introduced a model with accuracy of around 94% and short execution time. Another paper by Premadorfer and Campbell describes the approaches taken by 6 current papers and ensembles their network to achieve 75.2% test accuracy on FER 2013 dataset. One of these 6 papers is Learning Social Relation Traits from Face Images by John. They have formulated a new network architecture with a bridging layer to learn a rich face representation. The method achieves a performance of 75.1% accuracy through fusing data from multiple sources.
Now let's move on to the discussion of our objectives and the challenge that we have faced throughout this project. Our main intention is developing a smart AI to take the image as an input and therefore extract all the necessary features from that image by different CNN architectures. As a result of densifying it to the 7 layers, it can predict the label, in other words, the facial expression of the image. Main idea is improving the previously developed models and increasing the accuracy to the peak level. Therefore, we generated a new secret recipe to improve the previously developed so-called AI model to smart AI, which can possibly predict and do well. Our goal is adding new appropriate datasets, utilizing pre-trained popular CNN architectures, and using transfer learning on some models. But there are some problems. In order to do that, there are several points we should tackle. For the dataset part, for example, we need to choose mainly balanced datasets that are coming from the same distribution as baseline dataset. And we should also pre-process each new dataset to fit in our model. As we can see from this confusion matrix, FER is unbalanced, and due to the lack of disgusting face image, the predictions are mostly incorrect. For the models part, as we are using very deep neural networks with large amounts of datasets, it's highly likely to face such constraints that models can overfit. Also, computational resource may not be enough. As we can observe from the curve, the ResNet 50, which is trained on only the baseline dataset, is overfit.
One of the main issues we faced, as we said before, was overfitting. And in order to combat this, we performed actions on our dataset and we performed actions on our model. First up, for the dataset, we performed data augmentation on the FER set by doing random horizontal flips, random rotations, and random translations. We also added more data from the EffectNet and CK Plus datasets to have more samples. Next up was the actions on our model, mainly regularization techniques. We used dropout, L2 weight decay, and batch normalization.
Let me explain the results we've obtained. Our experiment is divided into 2 stages. First, we have been only using the FER 2013 dataset. It's entirely composed of grayscale images, and we've divided it into 3 parts: training, cross-validation, and test using this ratio. All the models we have been using were pre-trained, and the best performance was obtained from ResNet 50 by utilizing the concept of transfer learning, whereby it fully connected layers on the pre-trained CNN ResNet 50 layers. This loss curve is also obtained from the best perform model. We can see that the training error doesn't even seem to converge even if we pass more than 50 iterations. But since the middle iteration, the validation error started picking up. So this suggests that our data is overfitting. In order to alleviate this problem, as our second stage of our experiment, we have added some data augmentation and auxiliary data sets like CK Plus and EffectNet. We have divided them in the same way, And then again, we've utilized the concept of transfer learning or ResNet. And in this ResNet, we didn't add fully connected layers. We've only changed the last layer to 7, which is the number of classes. This is the additional model we've been using. And we have obtained the best accuracy from EfficientNet. All of them are pre-trained. From the loss curve, we can see that this loss curve is again obtained from the ResNet 50 pre-trained model. So even if there are some bumps in the validation curve, we can see that in overall it's decreasing. So our overfitting error has been somehow solved. What did we learn in performing this experiment? We have learned a couple of data pre-processing techniques. So FAIR 2013 was composed of numerical pixel values, and CK Plus and AffectNet were composed of JPG files. For FAIR 2013, we have utilized Torch Vision's inbuilt function, which is called image folder, to convert the numerical pixels into JPG files. But we have realized that some AffectNet images have been incorrectly classified to their label. So we cleaned some of the data by using CEDO labeled CSV files. We reclassified all the image to the correct labels. In terms of model building, we have gained a hands-on experience on how to fine-tune the hyperparameters of all the models we have tried. We examined and compared the accuracies of all the CNN models, because in theory, we have only know the mathematical intuition behind forward and backward propagation. But here we saw in our own eyes which model is performing better. We are able to diagnose overfitting from validation loss curve. And in order to do the error analysis methods, we used confusion matrix. But in order to use the confusion matrix, we had to load our models. So we studied how PyTorch saves and load models. And then by performing the confusion matrix, we have realized that we need a balanced data set in order to have the highest accuracy, because it turned out that the most misclassified image is the label, which has the least number of training examples, as you can see from our confusion matrix. So in order to learn from all emotions, it's highly preferable for data set to be as balanced as possible. So we have also indeed saw that ResNet 50 and EfficientNet are well suited for this task. These are the references we have looked through during this experiment. Thank you so much for your attention. Good luck on answering our quiz problems, and bye.